Hello guys, Assalamualaikum warahmatullahi wabarakatuh and a very good morning. Happy Ramadan. So today is 16 March 2024. I'm going to talk a little bit about Trasatti method. So before this, you have learned about the done method. That's for you want to calculate capacitive and also diffusion control process of your material if there exists an obvious redox peaks. So what if when you run your cyclic voltammetry, you can't even find very apparent or you can find a very distinct redox peaks. So you proceed with the contribution calculation using Trasatti method. So a little bit different between Trasatti and also Dunn method. Okay, so the title for today's presentation, I divide into a little bit introduction, case study, and also conclusion. So the introduction about Trasatti, the same thing about with done method. The only thing is if your CV mostly undergo the surface reaction and also diffusion. So you think from your CV, cyclic photomogram, the behavior of your electrode, you think that and you observe there is no distinct redox peaks. The redox peak is not very obvious, so you might think it might be pseudo-capacitive material instead of battery type material. That's why you jump into Trasatti method. So I will show you case study, some of the graph and also the calculation to get a full analysis on the Trasatti method and also the conclusion of the Trasatti method. Let's jump straight forward to the graph. Okay, this is my new project. It's about new composite material. As you can see from here, let me show you with highlighter. Okay, this is the specific capacitance. You need to know the specific capacitance value by the GCD and also the CV with scan rate and also various current density. However, from this, you cannot see anything. You cannot determine either it can be pseudo capacitor or it can be battery type. The only important thing is based on the graph, which is GCD, galvanostatic charge discharge curve or curvature, and also cyclic voltammetric curve. Okay, can you see from the CV here? This already optimized the potential window. When I prolong to 0.6, 0.7, 0.8, you just can observe a very straight line, so indicating oxygen evolution, so it's not good. That's why I put the potential from 0 to 0.5. So from here, I can see obvious redox peak. And from the GCD, I can't even see a plateau. So the correlation between current and also scan rate is almost linear. It's just a little bit distorted. That's why I proceed with Trasatti. Okay, when you don't have a very distinct redox peak, you don't have a plateau on your GCD, so you can proceed with Trasatti method to calculate the contribution. Either the capacitive contribution is dominant or the diffusion control is dominant. Okay, let's go to this slide. So this is important slide about the Trasatti method. First of all, you want to confirm you run the cyclic voltammetry like this in a multiple scan rate. We run at multiple scan rate. You can choose a lower scan rate, 1 to 5, 1 to 10, or you can vary to increase the scan rate. So first step, first run the cyclic voltammetry at different scan rate. This is the same step. So the step number one is the same step as a done method. So the B value just want to screen your material. So your material undergoes what? So when I run the B value at log scan rate, milliwatt per second, so log current, the y-axis in ampere. So what I observe is the B value is 0.74. We said that 0.5 below is battery type and close to 1 is EDLC, but in the middle, if you have 0.6, 7, 8, okay, in the middle, you have pseudo capacitive. Maybe it half battery type half ideal C, so the middle, in the middle. So when I observe the p-value equal to 0.75, so I decide to do the Trasatti method. So step number 2, no need to proceed with done method. Step number 2, what you need to do is you need to plot the capacitance farad per gram versus scan rate power of negative 1 over 2. When you plot this graph, so you use the correlation on the origin to fit the linear. So you get y equals to mx plus c. This is y, mx plus c. So this, your c, the y-intercept here, is your capacitance of outer layer. Because you decide, in this case, you have two types of capacitance, whether it's outer layer or inner layer. Normally at the surface, we call that the EDRC contribution, or we call that a capacitive contribution. At the inner layer, we call that pseudo contribution, or we call that diffusion control contribution. So for the first graph, you got the number of C, which is the y-intercept 620.43. This is the contribution of capacitive contribution. So in reality, what you got is you got the capacitance total equal to capacitance EDLC plus capacitance pseudo capacitor. So first step, the first graph will give you capacitance of EDLC. So now you want to find what is your capacitance of pseudo. Okay, so the third graph will teach you how to get that value. But it's not straightforward. This third graph will help you to get the total capacitance of your material can achieve at certain potential window. Okay, here the y-axis is 1 over C and your x-axis is scan rate power half in volt per second. So 1 over C, so you got, for example, you run your experiment at different scan rate. For example, 1 millivolt per second, 2 millivolt per second, 3 millivolt per second, 4 millivolt per second, and 5 millivolt per second. So you convert from millivolt per second to volt per second to make it easy. So for example, you have 0.001 until 0.005. Then after that, you got the value of capacitance at each scan rate. Okay, then you plot 1 over C. For example, your capacitance at 1 millivolt per second is 1000. So 1 over C equals to 1 over 1000. You got the value. Then you get a straight line plot by fit linear using the origin. Okay, so it's quite simple. So again, when you fit linear using your origin, you can get y equals to mx plus c. So now your y is 1 over c. Your mx is, you got the value, but focus on the y-intercept. Your y-intercept equal to 1 over c total. So you already got from graph number 3 is 1 over c total. So in this case, 1 over C total equal to 9 power of 9.04994 exponent negative 4. So from that, just use your calculator to get the value of C total. C total equals to 1 divided by 9.04994 exponent negative 4. Then you get your C total. Okay, then before you plot graph number 4, what you need to do is you find the C pseudo by having C total equal to C EDLC. I just put the acronym CE for CDLC and plus with C pseudo CP. CP. Okay, so now you already got your CP. By having that, for example, when you calculate, you got your C total is around 1000, 1000 minus your 620, then you got your C pseudo-capacitive, how much. So then you can go for the contribution ratio. This is quite easy, same with that method. Okay, however, for the Trasatti method, okay, for the Trasatti method, the contribution, diffusion contribution or capacitive contribution is the same for each scan rate. So if you run for 1 milliport per second, if 44% efficient, 2, 3, 4, all the same. That's the lacking for the Trasatti method. Okay, but the graph you can plot. The graph is the same thing, how to plot the graph. Just refer to the video of the done method, the graph is the same. The only difference is to find the contribution ratio. So this step is straightforward. You just use the graph, just plot two graphs, what is important. Capacitance versus scan rate power negative half, and also 1 over capacitance versus scan rate power half. From this both sides, you can get your C ideal C and also C total. From that, using the correlation that I show here, you can get the pseudo capacitance. Then after that, you can choose either one. This one I choose for diffusion contribution, means that I use the contribution of C pseudo capacitance. If you want to show the diffusion for the contribution for capacitive, you also can show from the graph. Okay, I think that's all. I hope it helped you to do your experiment. So not all the graph can undergo Dunn method, but some of them you can use Trasatti method. So I think it's quite straightforward. If you don't understand, just drop a comment. If I have time like today, I can do some explanation video. I think that's all. Hope you success in your journey and research. Okay, bye. See you again. Happy Ramadan.